In this video, we'll be going over another equilibrium problem where we can use a rice table to puzzle out different starting conditions. In this question, the equilibrium constant for the following reaction is 2.18 times 10 to the 6. You may be thinking to yourself that this is rather large. It is. That's why we're starting with some interesting information. If you start with a concentration of 0.255 molarity of the HBr molecule in an otherwise empty vessel, we need to find the equilibrium concentrations of all the species. Okay, so I'll go into my normal rice table mode. I'm going to start by rewriting my reaction. I notice that I have a 1:2 ratio between either reactant and the product. Okay. Then I also notice that I'm not starting with any of my reactants. This tends to freak out my students the first time they see this scenario, and they try to do some fancy math where they flip the reaction and flip over the K and do all sorts of extra work. You really don't need to do that. Just put zeros in the I box for the reactants. Now we are starting with a given 0.255 molarity for our HBr. Cool beans. Alright, now we don't have any other information to fit into my table, so I need to puzzle out how things are changing. I realize that some of my products are going to become reactants because there's really no other way to go. I do need to fill in some X values. See, I'm going to be adding my reactants in 1:1 ratios, but I have this pesky 2 here indicating that I'm going to be losing 2 times as much from my product side. Okay, now I'm going to add up the initial and the change columns to get my equilibrium columns. 0.255 minus 2x, x, and x. And now I'm ready for my equilibrium expression because I have algebraic expressions for all of my equilibrium conditions. So here's what we're going to do. We're going to write out my equilibrium expression. Always a good plan. It'll help you prevent errors in your math. And on some people's exams, this expression is usually a point. Okay, now let's plug things in. My K value is 2.18 times 10 to the 6, and my HBr values 0.255 minus 2x, not forgetting to square that expression. And then I'm going to have x times x on the bottom, and I'll go ahead and reduce that, or rather combine like terms, for my x squared here. Okay, now I'm feeling like there's a lot of squareds here. I could do fancy-pantsy quadratic equation stuff here, or I can just relax and square root both sides. This takes care of the squareds on the right side, and it makes my number a little bit smaller on the left. I'll end up with something that looks like 1476.48. I'm going to keep all my extra sig figs until the very end. And that's going to be equal to my regular expressions, but just not squared anymore. I'll multiply my x to the other side, getting 1476.48 times x. Simplifying. I don't really need parentheses here anymore. It's just kind of a force of habit. I'll add my 2x over to the other side, increasing my absurd number of x's to 1478.48 x. And now I can divide over that really fun number to get that my x value is equal to this super tiny number, 0.255 0.0000172. Now that's really tiny. You generally want to report your answers in scientific notation if they get that small. And now it's time to reread my question. And I realize I need to report my final concentrations. So in my calculator, I'm going to do 0.255 minus 2 times the x I found. And I realize that there isn't really a significant change. It's such a tiny number. So I will report my HBr concentration is actually still equal to 0.255 molarity. For the next two guys, both of them are equal to x, so all I need to do is write down their values. Both concentration of hydrogen and bromine are equal, and they are equal to my value of x, which in scientific notation is 1.72 times 10 to the negative 4 molarity. And that's how you handle a problem if you're given starting information that's for a product. As always, make sure that you practice plenty of examples so that you get used to all of these routines.